Okay, let's go ahead and get started. Good morning, evening, and afternoon, everyone, depending on your time zone, and thank you for joining us. Before we get started, I just want to mention that we have the Q&A feature turned on, so if you have a question at any point during the talk, you can go ahead and type it in there, and we'll answer them at the end. And closed captioning is also enabled for this webinar if you want to turn that on for yourself. I also want to remind everyone that if you want to suggest future speakers in this series, we have a suggestion form that you can fill out, and I'll put the link to that in the chat. And so without further ado, I want to introduce today's speaker. So Dr. Araki-san is a senior researcher and leader for the Research and Development Group for Seafloor Observatory at JAMSTEC. His research interest includes seismology and optical fiber sensing, and we are delighted to have him join us today to discuss his work in the Nankai Trough. So without further ado, Dr. Araki-san, the floor is yours.
Thank you for introduction. Here I will talk about measuring wide dynamic range behavior of the seismogenic plate margin by optical fiber strain, current and near future effort in the Nankai Trough. My talk today is based on our collaborative researches in our group in JAMSTEC and Dr. Mark Zumberg in Scripps. So here's a map of the Nankai Trough area, the margin of subducting Philippine Sea Plate into Japan Island, causing mega thrust earthquake every 100 to 150 years. The rupture zone of these earthquakes are outlined by red contour here, and the last large earthquake occurred in 1944 in Tonankai area, and in 1946 in Nankai area, resulting in severe damage to Japanese society by the strong earthquake motion and following tsunamis. Now, the seismic activity in these regions are fairly low, with exceptions of earthquake in Hyuganada area and magnitude 6.1 earthquake in Kumano in 2016. But with recent advancement of earthquake monitoring in the seafloor, we recognize swarms of slow earthquakes occurring episodically. With the most recent array of seafloor borehole observations, now we have strong confidence that these slow earthquakes are related with slow slip events occurring in the subducting plate interface, shown with this example of the episode in 2016. Here, the magnitude 6 earthquake in the plate interface triggered offshore slow slip event and propagated toward the trench, with very active swarm of slow earthquakes. We have record history of such triggered and recurring slow slip events by the borehole observations shown here. Now, we are aiming for monitoring these slow slip events in the wide area in the Nankai Trough subduction zone. We think that the fiber optic is very effective means of observe these phenomena in the Nankai Trough. Seismic waves from earthquake propagate and lead to dynamic strain change in the seafloor. If we observe a strain near the fault motion at depth also leads to deformation of surrounding crust, including of the seafloor. With these processes, we can detect and analyze fault slip at depth by observing strain of the optical fiber in the seafloor. We can think of many advantages of fiber optic strain. The most importantly, our optical fiber strain measurement uses interferometric technique and gives us significantly high dynamic range from picostrain to the tolerance of optical fiber itself, often of close to 1% strain. The interferometric measurement also assures high linearity and broadband response of the measurement, accurate from millisecond to years period. These characteristics are very much suited for our observation targets. With distributed optical fiber sensing techniques, we can also expect very wide area coverage to 10,000 kilometers and high resolution to centimeter, which means that really large number of measurements are obtained. Now, I talk about the application to seafloor deep borehole observation. We are planning to expand seafloor borehole observation from Kumano area to the whole Nankai Trough with 3 new seafloor borehole observatory installations, shown by these red triangles, which target potential shallow slow slip events from our over 10 years observational history of offshore slow earthquakes, shown by the yellow area. With the new borehole observatory deployment, we developed a new deep seafloor borehole observation system outlined here, in which we can observe pore fluid pressure and fiber optic strain 500 meters below the seafloor. These measurements should cover our observational target from slow slip event, micro earthquake, to large earthquake in the Nankai Trough. Because these measurements have significantly high sensitivity and high dynamic range as well. Because we aim for long-term, multi-decadal observation with the new observatories, we introduced no electrical and mechanical components, which in many ways fail for sure. All the seafloor components are exchangeable, so we can continue observation for many decades. The data is streamed to seafloor cables such as DoNet to realize long-term monitoring in real time. Near the bottom of the borehole observatory, we installed a fiber optical sensor, which integrated two interferometric fiber optic strainmeters, which measure 200-meter long fiber cable helically wound in 150 millimeter diameter cylinder for area strain measurement. In parallel, we have integrated 4 sets of 200-meter long fiber for distributed optical fiber sensing for various distributed optical fiber sensing technique to measure the fiber in deep seafloor borehole. The first installation of such new borehole observatory was performed in November 2023 by drilling vessel Chikyu in off-key peninsula, the Nankai Trough, where we drilled 500-meter deep borehole by Chikyu and then constructed almost 500-meter long sensor string to connect bottom hole sensor and the seafloor components, terminating cable and hydraulic tube for observation. Then, soon after the deployment by Chikyu, we performed the connection to DoNet 2 by ROV Hyper Dolphin in January 2024. With cable laying system we have been using to construct all other DoNet seafloor sensors. We successfully linked the borehole to DoNet in January 2nd, 2024 to start continuous long-term real-time observation by the deep seafloor borehole observatory of Key Strait, Nankai Trough. Here are the records from borehole observatory. We can clearly see the response to ocean tide in both the borehole pore fluid pressure and fiber optic strain measurements. Next, I'll show the response of borehole observatory during two major earthquakes, compared with data from a nearby seafloor fiber optic strainmeter array, which I'll talk later. On the left is a record from large earthquake in Taiwan on April 3rd of last year. You can clearly see the surface waves dynamically straining both the seafloor and the borehole. The responses indicate that the borehole fiber is observing area strain in the deep seafloor. On the right is the response to another large earthquake, this time closer to the observatory in the Bungo Strait. In this case, the seafloor strain records were distorted due to strong motion in the soft sediment on the seafloor. However, the borehole clearly recorded the earthquake, demonstrating the very wide dynamic range of the borehole fiber strain observations. Initially, the borehole fiber optic strainmeter exhibited rapid strain change due to cement hardening. However, after 1 year since installation, the system has stabilized significantly, and it is now a condition suitable for detecting slow slip events. Next, I talk about seafloor fiber optic strainmeters. The seafloor fiber optic strainmeter is an instrument measuring 200-meter long optical cable laid in the seafloor with laser Michelson interferometer to get seismic to geodetic strain change in the seafloor. We installed the instrument in 2019 in the Nankai Trough by the ROV, as shown here, and connected to DoNet submarine cable network. We started continuous long-term observation since then. And in 2022, the instrument detected slow transient strain change for a couple of weeks of about 0.7 microstrain, like here, synchronized to the period of local swarm of slow earthquake or very low frequency earthquake, VLPs, as shown by the panel below. If we look at strain record for each local VLP, like here, we observe interestingly not only the seismic waves from VLPs, but small slow strain steps with each event, such as here, about 20 nanostrain. This is very unique observation because the distant VLP event didn't show such steps, but only seismic wave like above. Further, the observed steps have several different patterns, like here, contraction, then extension, and extension. If we plot these observed patterns in the map, we notice clear correspondence to the focal mechanisms of the event and the relative location of the strainmeter. Therefore, these observations strongly suggest that we are measuring deformation of the crust directly caused by the fault dislocation at depth. In other words, we are directly measuring fault motion at depth with the Seafloor fiber optic strainmeter. This observation also suggests that the long duration transient also suggests the existence of larger and slower fault slip backgrounding these small VLP event fault patches, like the conceptual cartoon in here. Although it is very difficult to model the fault motion from a single point strain measurement. Therefore, we are currently working on deploying array of fiber optic strain observation in the Nankai Trough. This includes a 3-component array of key slate, as well as single component strainmeter in the Kumano region, collocated with existing borehole. Additionally, we are preparing for the deployment of another array in Hyuganada area later this year. Next, I will talk about our development in distributed optical fiber sensing. Our research spans from technical development for broadband wide dynamic range distributed optical fiber sensing techniques and verification of the new techniques with a 120-kilometer long submarine cable of Muroto to our continuous long-term observation for monitoring and analyzing Nankai Trough seismogenesis. Here, we developed broadband DAS, which significantly improved long period performance compared to commonly available DAS interrogators using a stable laser as the stable optical length reference of the measurement. As shown here, the improvement is as much as 40 dB and reaching very close level to the fiber optic strainmeter, which I showed previously. Here's an example of the broadband DAS record with 120 km of Muroto cable, showing clear seismic wave trends from distant earthquake, as well as small deformation of the seafloor caused by a few millimeter high infragravity wave in the ocean. This suggests our ability of detecting small tsunami by the instrument. Indeed, we detected tsunami in 2023, and its detailed explanation is presented in Tonankai and Araki paper in GRA. We are also developing another distributed optical fiber sensing technique known as TWCOTDR or RFS. TWCOTDR is a distributed optical fiber sensing technology that, like DAS, analyzes Rayleigh's backscattered waves. However, instead of analyzing phase differences, it focuses on the Rayleigh intensity pattern, RIP, in the optical frequency domain. In contrast to DAS, which detect optical phase differences between scattered waves separated by a certain gauge length, and lacks a deterministic phase at each location. TWCO-TDR offers a more stable reference. One of the key issues with that is that even a single-phase tracking error can lead to significant inaccuracies in long-term observations. TWCO-TDR and RFS utilize the optical frequency-dependent Rayleigh intensity pattern, RIP, which is defined by the fixed spatial resolution of scatterers within a region illuminated by the optical path. This pattern is deterministic and does not change over time. However, it shifts in optical frequency when local strain or temperature conditions change, allowing us to detect these changes. This principle is similar to Young's double-slit interference experiment. Interference between Rayleigh scatter waves determined by the geometry of scatterers produces unique and stable pattern. When strain alters the geometry, the interference pattern shifts in optical frequency. Since spatial resolution is determined by the optical path length, these techniques achieve very high resolution, typical around 1 meter or less. Moreover, they allow intermittent measurements, for example, hourly or even yearly, which is not feasible with DAS. RFS technique further improves upon TWCO-TDR by employing a sharp laser, enabling much faster evaluation of the frequency spectrum. Here's an example of the TWCO-TDR measurement with the Muroto cable, showing two measurements in 22 minutes interval at point 64.9 kilometers offshore. The Rayleigh intensity pattern resembles with each other, showing very sharp correlation near zero frequency like here, suggesting persistence of cause of local interference in the optical fiber. The frequency shift of the RRP directly related with strain change between measurements, and shown by the panel here, showing consistent and variety of strain change occurring in the seafloor up to 0.2 microstrain in this example. We can repeat the TWCO-TDR measurement to find long-term change of the seafloor strain in wide area, as shown by this example for a week up to 75 kilometers from the shore. The pattern of diurnal and daily strain change observed here are mostly representing seafloor temperature variation that we verified from thermometer data deployed near the cable by ROV. The optical fiber in this case regarded as very high resolution seafloor thermometer array every 1 meter to the distance. As a next step in fiber optic sensing technology, we are now looking at using entire submarine cable systems, not just for data transmission, but as sensors to monitor cluster activity. For example, cable like DoNet and NNet shown on this map could be used to measure strain distribution along their full length. We are also exploring the idea of using commercial submarine telecommunications cables, both domestic and international, for this kind of observation. This approach could allow us to monitor how tectonic plates are coupled together across wide seismic zone in real time. Now, I've talked about wide area observation. Now, I talk about microscopic scale application of fiber strain in the deep seafloor borehole observatory in the Nankai Trough. Currently, unfortunately, we do not have any interrogator for distributed optical fiber sensing in the seafloor. So we connected shipboard interrogator to the borehole by ROV umbilical to observe the coil fiber at the bottom and the fiber section connected bottom hole sensor and the seafloor. In our experimental observation with the borehole observatory by ROV, we had to compensate the optical loss in the ROV umbilical by optical amplifier. I do not go too much technical details here, but we observed total 1.7 kilometer sections of the optical fiber in the borehole. We performed two types of distributed optical fiber sensing here, DAS and RFAS. Here, I presented the results of DAS observations. This is a 2 minutes recording from the DAS system, showing data from the seafloor to the bottom hole sensor, and back to the seafloor, all spliced together in series. In the section of the bottom hole sensor, we have the first three 200-meter sections of strain-insensitive fiber, followed by a strain-sensitive section, as shown here. We observe microseismic strain changes with a period of a few seconds in most of the vertical fiber sections. These changes are also visible in the strain-sensitive part of the borehole fiber sensor. Notably, the amplitude of the strain-sensitive sections is smaller than the vertical fiber sections, and the polarity is opposite. This suggests the borehole coiled fiber is responding to area strain near the bottom of the sediment layer. Next, this is RFAS measurement result. We performed intermittent observation by RFAS while the borehole is connected by ROV umbilical. This is the observed strain change in 2.5 hours interval during the experiment. During the period, we have change in tidal loading in the seafloor. Therefore, we consider the observation represent a sediment deformation due to seafloor tidal loading. Notably, the vertical fiber section, we only see strain change where the cable is cemented. This strongly suggests the cable is well responding to the deformation of the surrounding sediment. Similarly to that observation, we have almost no change in the section of strain-insensitive coiled fiber, and smaller and opposite sign of strain change to the vertical section. This is really encouraging result because unlike that, this is obtained with a very high 1-meter resolution in space. Interestingly, when we overlay the result with seismic section of the borehole, the strain response of the vertical section has some correlation with the strata in the sediment, such that more compliant response in the shallower depths and repetition of smaller strain responses. It seems that the response reflects local stiffness structure of the sediment. This itself may not sound very important, but we are thinking about drilling through a seismogenic fault of slow slip event and observe processes in the vicinity of the fault in the future, where the dynamics could concentrate in very narrow zone. So this marks the first feasibility of such future project. Finally, we started development of a system jointly analyzing such seafloor network data from DoNet and DAS in real time. Here's an example of the result from the joint real-time analysis system, showing so many aftershocks analyzed. Many of the events was not analyzed by Japan Meteorological Agency. Here is another example of detection of triggered tremors in the Nankai Trough after the Noto earthquake in January 1st, 2024. Here, we show the record from DoNet broadband seismometer and DAS. In many DoNet stations has no response due to the strong ground motion during the Noto earthquake when the swarm of tremor occurred. But DAS didn't, proving great potential of DAS monitoring small aftershocks after the large earthquakes, which we should do in coming large earthquake in the Nankai Trough. To conclude, We are developing a seafloor observation network in the Nankai Trough that integrated borehole measurement, seafloor fiber optic strainmeters, and distributed fiber optic sensing. This allows us to monitor and analyze interplate dynamics across a broad spatial scale. These technologies are not limited to the Nankai Trough, I think. They can also be applied to other subduction zones, such as Cascadia. We are especially interested in building international collaboration that combine borehole observatories and fiber optic sensing technologies. The data we've collected in the Nankai Trough so far shows great potential, I think. To further advance these techniques and explore new directions in data analysis, we are planning to recruit a postdoctoral researcher in the near future. If you are interested, please feel free to contact me. My address is here. Thank you very much for your attention. Thank you very much.
Thank you very much. If anyone has any questions, we have time to take those questions. So please put them in the chat or in the Q&A section. Thank you so much, Araki-san, for such an awesome talk. We have one question from Surui Sie. Is there drift in this type of observation? How to evaluate that?
Drift on which part? Is it the borehole or the fiber optic sensing in the seafloor cable? So if we speak about the borehole observations, we have an effect of thermal condition change over long years. And also the cement consolidation also affect the strain change in the borehole. So this is the major processes in the drifting in the borehole sensor. But the process is, as we experienced, very slow and minor. And I don't think that this is problematic for the detecting slow treatment. And on the seafloor fiber optic sensing, our fiber optic sensing technique all utilize very stable measurement reference. For example, our Broadband does utilize the cavity locked laser, which has optical frequency drift smaller than most of the tectonic strain change if we compare the rate change. So this is very stable compared to our expected tectonical rate. And also in TWCO TDR or RFS, we calibrate optical frequency by the gas reference, molecular reference. So we confirmed that over long years, our optical frequency of measurement reference does not drift over time. This is the current idea.
Thank you so much. Let's wait a little bit to see if we have any more questions. If we don't have any more questions, I want to remind everyone that you can feel free to send us an email if you think of something after the fact, and that a recording of this talk will be up on the SC4D YouTube channel if you want to rewatch it or share it with your colleagues who weren't able to make it. Thank you so much, Dr. Araki-san, for this amazing talk, and thank you to everyone who joined, regardless of the time zone that they're in. We really appreciate you coming to join us this afternoon, evening, or morning. Thank you all, and I hope you have a great rest of your day.
Thank you very much.